Oh, all right. Good evening, everyone. Good evening. Good evening. Glad to see you all here. Bushy-tailed and bright-eyed. I like that. I like that. So today, number 4 is we're going to cover the analysis of covariance. Okay. So the first day we looked at what we did when we compared two groups on a continuous variable. Then the second day, we looked at what we did when we compared 3 or more groups on a continuous variable. Then the third day was examining what we would do if we had 2 or more independent variables of 2 or more groups. Okay. But today we're looking at comparisons, but we're also looking at controlling for covariate. Okay, so this is the analysis of covariance. All right. So I'm going to start out with a conceptual review, how to formulate the research questions, how to enter the data, evaluating the assumptions, linearity, homogeneity of regression slopes, homogeneity of variance, and then how to interpret, and then how to report the Ancova. Okay. So it's called an analysis of covariance. And essentially what we're trying to do is we're trying to look at the relationship between an independent variable to see if there are any significant differences between groups of an independent variable on a dependent variable. And this is typically used when you have a pre and post test. Okay. So if you're trying to compare differences between groups when you've had a pre and post test. So for example, in this instance, we're trying to determine if uh, there is a significant difference in depression scores among 3 different intervention techniques. Okay. So one is counseling and journaling therapy, one is just counseling, and then one is just journaling. So you have a combination of the two together, counseling by itself, and then journaling by itself. But what we want to do is we want to control for any differences that existed before the people actually took the different interventions. So the way this would, so this is just one example. So the way this would work is everyone would get a pre-test in depression scores. Okay. And then they would be randomly assigned to one of these 3 groups. And then after the counseling sessions, then they would get another depression score, the post test. Now, in order to accurately determine if the treatments had an effect, we would have to neutralize the differences in depression before these people actually took the intervention, right? So some people may have had higher depression, some people may have had lower depression. So what we do when we have a covariate is we reduce the differences so that everyone starts at 0. So we do that mathematically. So we remove the effect of the differences in the pretest scores, okay, so that everyone theoretically is at 0. So there are adjustments made to the mean so that when you have the post-test depression scores, you're just looking at the effect of the interventions themselves. Okay, does that make sense? So you have a pre-test, intervention, and then a post-test, but you want to remove the differences in the pre-test so that you just see the effects of the post-test. Does that make sense? All right, so now let's look at a business case. So we have J Mobile, and essentially what we want to do is we want to see if there are significant differences in the groups of the sales force who took the sales force training offered by the company and those who did not, right? We want to see if there's a significant difference in Salesforce satisfaction score. So essentially what we're doing is we're having their clients rate them on satisfaction. But if you think about it, these satisfaction scores could be affected by something else, right? And what could that something be?
Years of experience in the field.
Years of experience in this field. Spoken like a true salesman. So what you
he gets a gold star.
Yeah, he gets a gold star. He gets a gold star. Because here's the thing. If someone has 30 years of experience and someone has 1 year of experience, but the person in the 30 years of experience didn't take the sales training and the person who has 1 year did take the sales training, there could be some biases there, right? So what you want to do is you want to eliminate the effect of any years of sales training so that everyone is starting at 0, right? Everyone, mathematically, you're adjusting the mean so that everyone is starting at 0 so that you're only looking at the effect of the sales force, the sales training, whether or not they took the training, okay? This is what we call analysis of covariance. So essentially how this works is that when you would use this when you say to yourself, okay, are there other things that could influence Salesforce satisfaction scores, right? Salesforce satisfaction scores, and that's years of experience. So but up here, you would ask yourself, are there other things that could influence post-death depression scores? Well, if the person was already depressed, that might affect their scores, whether or not they, were in any particular group. So the covariate is essentially anything that could provide an alternative explanation to your outcome. Okay, you want to control for that. Does that make sense? Does this make sense conceptually why you'd want to control? Because without controlling for this, you really don't know if it's the sales training or whether it's their years of experience. Does that make sense? Okay. So
is there a limit to the number of control variables you can have?
No, there's no limit, but they shouldn't have a high correlation to one another. They should not. They can't have a high correlation to one another. And the reason that is because if they are highly correlated with one another, then you really don't know what you're controlling for. You have to have something that is independent, relatively independent.
A different dimension.
Exactly.
Okay.
Exactly. Sense. Exactly.
And then if you're studying, anything with human behavior, wouldn't, gender, age, for example, like always be a covariant you'd want to control for?
It depends. It depends on what you're looking at. If gender could explain a particular outcome, then yes. So it has to be sort of theory based. What you would probably do to determine if it should be a covariate is to look at the relationship between the covariates before you actually have it in an Ancova, right? So for example, let's say, I wanted to see if there were significant differences in gender groups on Salesforce satisfaction. If I saw that there was, then I would add that as a covariate. Does that make sense? Yeah. But so you would test it first to see whether or not there's a relationship. And then if there was a relationship, then you would add it as a covariate.
Probably test it with an analysis of variance?
Analysis of variance, but since it's only 2 groups, you could use a t-test as well.
Yep, yeah, right.
Yeah, but analysis of variance is great. You could still use it with analysis of variance because then you wouldn't have to go and calculate the effect size by hand, right? So either way, okay? All right.
Jacob, is this also known as confounding factors? Are these also known as confounding factors?
Yes, theoretically, they could be confounding factors, absolutely. Because they could be another way of explaining your outcome. if they're not controlled for, right? So now, interestingly enough, this, and it's, I don't want to get too deeply in it, but this is like a regression, okay? This is very similar to a linear regression, a stepwise linear regression, where you actually have one independent variable here, and we'll get into that. I don't want to get too deep into it, but it's basically a type of regression, right? You have one IV here, and this is your DV, and this is another control variable. So you would actually put this in first, and then you would put this in second in the stepwise regression. But Ancova is doing that for you all simultaneously. Okay. All right. So, any other questions? So again, if you believe that there's something that could explain the outcome, another alternative explanation to an outcome, you would want to test it. And then if you found that it was, then you would actually put it in. Okay.
So Jacob, it basically depends upon our question, right? Because here we can also run factorial ANOVA, checking both sales training and years of experience for sales force satisfaction scores.
Yes, you could. So Salesforce, yes, you could run an ANOVA here. But this is a continuous variable, right? So with ANOVA, your independent variables always have to be categorical.
Right.
They always have to be categorical. So whenever you have a combination of categorical and continuous variables, you should run a regression.
Gotcha.
Right? And let me tell you a little secret. You can run regression on anything. All these tests that we're using, you can run a regression. Any test you want to run, t-test, ANOVA, Ancova, MANOVA, you can run a regression. But here's what happened. There was a split in statistics. I think it was psychology. There was a split. Some people took the perspective of, oh, we just want to look at relationships. And then other people says, yeah, we want to look at relationships, but we want to look at them from the perspective of groups. And that's how you have a shift with ANOVA and a shift with regression. But regression can run everything. But the ANOVA people were like, yeah, we don't like regression. We like ANOVA because it's cleaner. You know, we can look at our groups. We know the means, and you have to do too many calculations. So that's why we have two different things that actually do the same thing.
Gotcha.
Okay. All right. So we have the Ancova. Now it's a one-way Ancova. So let me ask you this. If we had a two-way Ancova, what would we have? Remember what we talked about last night?
Yeah.
One-way, two-way, three-way?
So
multiple independent variables.
Yes.
Okay.
Multiple independent variables. Multiple categorical independent variables, right? So if we add it, so then we'd have to determine whether or not gender was going to be an IV or was going to be a covariate, right? So if you decided to do that. All right. So let's come down here and let's look at the research question. Is there a significant name a variable effect on some measure when controlling for a covariate? So in this example, is there a significant training status effect on sales force satisfaction scores after controlling for years of sales experience? And the null hypothesis, there is no significant training effect on sales force satisfaction scores after controlling for years of sales experience. And then this one is, there is, not no. So there is, let me just fix that right now. There is a significant training status effect on sales force satisfaction scores after controlling for years of sales experience. Now, the requirements, your dependent variable needs to be continuous. Okay. Your independent variable needs to be categorical, and it needs to have at least 2 groups. When you see 2 levels, that means groups. Okay. The covariate needs to be continuous. Okay. Now, if you only have 2 categories where you have with gender, you can still use that. But once you have 3 or more categories, you can't use that as a covariate. Okay? You can't use it as a covariate because it's not continuous. So that's the only way that you can get away with it not being interval or ratio, if you only have 2 options in your covariate, because you already know what the 2 options are, male or female, so you know what they are. All right. So the assumptions, linearity, because analysis of covariance is a type of regression, but it's just in ANOVA form. So ANOVAs are considered general linear models. So actually, when you run ANOVA in SPSS, you can get an R squared, you can get an intercept, which is the B. You can get all that. You can ask SPSS to provide all that for you. In fact, I believe they show it to you at the bottom. So linearity, and I'll show you how we do that. Homogeneity of regression slopes, which means that the relationship between the covariate and the dependent variable has to be relatively similar. Okay. They can't have an interaction where one's going in one direction and one's going in another direction. Okay. And the reason that is because is that if you're going to control for the covariate for all of the groups, they should have the same relationship, right? One shouldn't be negative and one shouldn't be positive, right? Because it won't work that way. It's assuming that the relationships are similar. And then homogeneity of variance, which is, as we know, the spread of the data, right? With the bars, we're looking for the spread of the data to be relatively similar for the independent variable. All right, so now let's go and take a look at what we're doing here. All right, so we've got our data file. Okay. And then we've got we have our Ancova. Is this the cheat sheet? I believe it is. No, it's not. Hold on one second. So essentially what we're going to do first is we're going to check for linearity. Okay. We're going to check for linearity. And the way that we do that is as follows. Let me just open this up for you. Data analysis, Ancova. All right.
So, Chekas, I just want to confirm, you said that we can use categorical variable as a covariance if they just have two groups?
Yes, 2 categories, right. So male and female, theoretically, it's still continuous because it only has 2 options, right? If you get 3 more groups, then it's acting like a label because there's no linear relationship, right? If it's just 2 groups, right? Just like you can run a correlation on gender, right? Because you know what the 2 options are. But once you get into 3 or more options, then the relationship is not linear because those are categorical.
Now, if you want to add gender along with other independent variable, that can become a 2-way Ancova?
That is correct.
Now I'm getting it.
That's correct. So you can, and I'll show you once we go through it where the differences are whether it's an independent variable and whether it's whether it's a covariate. Okay. All right. So if you look along here in the cheat sheet, just move this to the side. You can just follow along at your pleasure. So the first thing we're going to do is we're going to check for linearity. So linearity is we're going to look at a graph. Go to legacy dialogues. We go down to scatter plot. Okay. We go to simple scatter and we go to define. And then we come over here. And then what we're doing is we're going to put the dependent variable into the y-axis. So the dependent variable, the measurement variable, the thing we're measuring is satisfaction, right? The satisfaction ratings on the Salesforce. And then in the X, we're going to put in the covariate. The covariate, which is years of experience, the thing we're controlling for, okay? And then we're going to break the relationship up by our independent variable, which is the groups, whether or not they had the training, okay? Whether or not they had the training. And then we're going to click paste. And we're going to highlight this and run it. So this is what I was talking about when you want them to have the same slope. Pretty much the same slope. Okay. So now the blue is the relationship between the covariate, which is years of experience, and satisfaction ratings for the training group. The green is the linear relationship between the no training group and satisfaction on years of experience. Linearity for this assumption, we want these to be linear. We don't want them, we don't want a curve, we don't want the things in blue to go like this. Okay? We want them to be linear. Same thing for the green. We don't want a shape like this. We want a shape that's linear. Okay? So we can actually look at this by doing this, by double left clicking the mouse and then going under elements and then saying fit line to subgroups. Okay. And then we're going to say uncheck attach labels because we don't want this right here. We don't need that because it's just getting in the way. But we see here that the relationship is linear. It's not curvilinear. The line of best fit is linear. Okay. So we have not violated the assumption of linearity. Okay. So let me just do this. All right. Now, the other thing that we're looking for is the homogeneity of regression slopes.
Jacob, how did you get those lines to show up again?
Sure, I went to elements, I double clicked and went to elements and then fit line to subgroups.
No.
You don't have that?
No, I don't seem to.
Okay, here's the thing. Right on the screen, there's these things on the bottom.
Yeah.
Right here.
Yep.
And the second one says add line at subgroups.
Ah, yes.
So you don't have an elements at the top?
It's a little tiny chart, but it does have it has exactly what you're pointing at. So
Okay. All right. Now, so let me just make this a little bigger. All right. Now, so linearity, we see that the relationship between both groups is linear, right? So that's number one. Homogeneity of regression slopes, right? It's a big fancy term, but we can break that down. Homo means the same. Regression slopes. These lines are the regression slopes. Okay. This is the regression slope For the training group, this is the regression slope, the green line for the no training group. Now, if these lines cross, they are not homogeneous, right? Remember we saw yesterday where we had an interaction and the lines were crossing? Remember when we were looking at the independent variables, we had two independent variables, and we saw that if there was a significant interaction, the lines were crossing. Like we had three groups and then they crossed, like I think it was on race. I think males, the men were
It
the
was
men were
age 18 to 34 or something like that.
yeah, exactly, right.
Yeah.
So on one group the males were higher, but then on the other group the males were lower because the lines crossed, and then on the third group they went back to the same. Here we don't want an interaction. We don't want a significant interaction because we want the slopes to go in the same direction, to be relatively parallel. Now we see that they're at some point in infinity they may cross because it looks like they're doing that. But I want you to take note of this because right now they're not crossing. Okay, they're not crossing. So visually we see that there is no violation in homogeneity of regression slopes. Okay, so here we have no violation, no violation.
I'd love to know what my peers think, because I feel like in Phil's class, he would have said there was an interaction here because the slopes aren't parallel. This is a specific question that I asked him during class because I thought they had to cross on the screen, and he says, no, you know that they are going to cross because the lines aren't parallel.
Okay, I'm going to show you.
Eventually they will cross.
Yeah.
The fact that they're not crossing on this display is just a function of the scales.
Right,
Yeah.
but it's also a limitation of the data.
Mm.
Right?
Mhm.
So if you had infinite numbers, they may cross.
Mhm.
Right? But for this analysis, for our analysis,
Mhm.
it's not functioning as an interaction. So
Okay.
I'm going to show you how to prove that statistically. See, here's the thing about people. You got to stay up on the latest research on statistics. It's okay. It's okay. Hey, I'm going to show you a trick so you can go back and tell your professor, oh, wait, professor, there's something else that you can actually do this, because Ancova is a robust test. So even though the lines are going to cross somewhere else, there's another test that we can do to determine, in fact, that even if it does, we're still okay. I'm going to show you that test. You got to stay up on the research, people. You got to stay up on the research. Okay. All right. So we have no violation in linearity. Okay. All right. So no violation in linearity. So now what we're going to do, oh, I love this. I'm so glad you brought this up. It's so beautiful. So now we're actually going to run an interaction term to see if in fact the interaction is significant. All right. So now we're going to go back to our data. So now we're going to go back to our data. And we're going to say, okay, we're going to test for the interaction. We're going to test for homogeneity of regression slopes. And what we do is we go here and we act like we're going to run it. Okay. We act like we're going to run it. So we're going to put in the dependent variable, which is satisfaction rating. We're going to put in training, which is the independent variable. So we're going to put that in the fixed factors. And then years of experience goes into the covariate, right? So Payush, this is where you would determine if something's going to be a covariate or whether it's going to be an independent variable. Okay. All right. So now we're going to run the model. We got to run it a little differently because we have to create an interaction term. So we're going to, so let me just, I think I went too fast. So click on model. And I'm going to create a custom model. We're going to move this over. We're going to move that over. Okay. And then we're going to highlight both of them. Click the first one, hold down the shift key, and then highlight the second one. And now you have an interaction term. So this is the term that is going to tell us if there's a significant interaction. Okay. I'm so happy right now. So that's all we have to do. And then we're going to click paste. And then we're going to highlight this and we're going to run it. All right. So then we come down here to this table. And we see here, so we've got training, right? We see that training is significant, right? Training status is significant. And years of experience, the covariate is significant. But guess what? So is the interaction term, right? So your professor was like, yes, see, this is, you can't, this, we have a situation here. We have a significant interaction. See, eventually this is going to cross. But here's what they forget. And here's why they need to keep up with the research. Ancova is a robust test. That means that they've done an infinite number, thousands of simulations, changing the values of the data. And a robust test is basically saying that under certain constraints, even if you have violations, your answers are going to, your p-values are going to be relatively similar. So a robust test is one that even when violations are present, it will give you a p-value that is plus or minus 0.02 of the true p-value. So if the true p-value—
I'm sorry, Jacob, can you just repeat that again one more time?
Sure. The definition of a robust test means that even in violations, when there are violations, that the p-value is going to be within plus or minus 0.02 of the true p-value. Okay? Now,
Okay.
there is this guy named Dr. Wu who did a computer simulation on the Ancova. And he says, let me prove to you that this is not a problem. So essentially what we're going to do, the Wu test of, it's called the Wu test of robust Ancova. And this will tell us basically, even though we have a violation, if we have to worry about the violation. So Wu basically said through his computer simulation that as long as the difference in the beta scores of the two groups is less than 0.04 or 0.40, we're fine. So let me show you. Let me show you how to do the Wu test. Okay. So the first thing you do, and I have this inside the cheat sheet. So now you can go back and tell your professor, oh, wait, there's a Wu guy, Dr. Wu, 1984. He's got something for you, professor. So, okay, so you go to split file, and then our grouping variable, you click on compare groups. Our grouping variable is training, right? So we're going to split this into training, and then we're going to click OK. Now what we're going to do is we're going to run a simple regression where we have the dependent variable and the covariate, right? The dependent variable and the covariate. The covariate is now going to be in the independent samples group. And then we run this. We're going to click paste. And then we highlight this. And we run it. And basically, if the difference between this right here and this right here is less than 0.4, we're fine. The interaction is controlled. The interaction is not a problem. So if the difference between your betas is the absolute value of 0.4, less than the absolute value of 0.4, you have adequately, the Ancova has adequate control for the violation in this assumption. And I have the reference for you in the cheat sheet. So, you know, if you want to take that back to your professor tomorrow, you can. Okay. All right. So now that we know, right? Because if you subtract these, right, it's really simple. It's like 940, 922. What is that? 28? Yeah. Was 20, yeah, 38. No, 28, 28. So the difference is point oh, 0.028, which is far less than 0.40. Okay?
Can you go back a little bit again and tell us what this is telling us?
Yes, yes. Okay, so what this is telling us is this. When we looked here, these are regression lines, right? These are regression lines. This beta is telling us the relationship between no training, between the ratings and the experience, right? So think of it as a correlation, okay? Think of it as a correlation. And basically what these regression lines are saying is we want the relationships between the satisfaction ratings and the years of experience to be similar for both groups, right? The interaction term tells us, hey, there's a problem. They're not very similar, right? The relationships are not very similar because these betas are like correlation coefficients, right? They tell us the relationship between two variables, okay? And what we see here is that these beta coefficients are very similar, even though we get a situation that tells us, oh, they're not similar here and they don't look similar somewhere later on down the road. When we look at the actual correlations, because what we did is we ran a correlation between, we ran a regression between, this is what we did, right? So when I went to analyze regression, linear, and put years of experience and SAT rating, that's this, those are these lines right here. Okay, so this 0.940 corresponds to this line right here. Okay, this 0.912 corresponds to this line right here, the green line. Now, one of the problems with checking for violations in the homogeneity of regression slopes is it's dependent on the size of the sample. So the larger your size, the more likely you're going to see a significant difference, even if one doesn't exist. That's one of the weaknesses of checking this way. That's why Wu went on the computer, ran all these simulations. He was like, hey, there's a better way to do this. And this is it, right? Because now we actually see the betas. We see it here, they're not crossing. So we say, okay, that should be okay. It looks like they're going to cross somewhere down the line. But when we actually look at the relationships, they're very similar. This does not indicate that the relationship, that these lines are very different. Does that make sense? Because you got 0.94 and 0.912. So this corresponds to, let me just go back here, 0.94. So this is 0.94 and this is 0.912. Those aren't very different at all, right? Those aren't very different at all. So because of the Wu analysis, we can say that homogeneity of regression slopes is not a problem. We have adequately met the standard to run the Ancova. All right. So it's basically three ways. So think of it this way. Think of it this way. There are three ways to check for homogeneity of regression slopes. One is the eyeball test, right? So this is the eyeball test. That's the least sophisticated. Then the second least sophisticated is by looking at the interaction term, right? Because the interaction term can be affected by sample size. Because if I was to lower the sample, it probably wouldn't be significant, right? So that's the second way. But the best and most reliable way is Wu's analysis, Ancova, the robust Ancova analysis, okay? A lot of people don't use that because they don't know about it, because they don't keep up with the research. But I sent you the reference so you can use that. All right. So is everybody with me? I know that was a little technical. Is everyone with me? Does anyone have any questions? It's okay. There's no bad question. Yes, go ahead.
So can you go up on that graph, please?
Yes.
I just want to understand this in a very simple language.
Yes.
So what we are saying is that the satisfaction rating and training
Yes.
have a correlation, linear correlation. Like people who are trained have a better satisfaction rating. People who are not trained has a lower satisfaction rating, and it does not depend upon the years of experience.
Okay, what this graph is telling us very simply is that there is a linear relationship between satisfaction ratings and years of experience for both the training group, the line is blue, and the non-training group.
Okay.
That's all it's saying. We can't derive anything else from this.
Okay.
Right? These lines are just saying, the only thing we're trying to see here is, are these lines going in the same direction and are they relatively parallel?
Okay.
Because we see that there is a linear relationship between satisfaction ratings and years of experience for the training group. And we see that there's a linear relationship between satisfaction ratings and years of experience for the non-training group.
Okay.
And statistically, the betas being less than 0.04 difference confirms the linear relationship.
It confirms that the lines are not crossing in a way that is
interaction effect. Okay.
Yes, there's not that the interaction effect is not a problem. Okay, and it's not 0.04, it's 0.40.
0.40, correct.
And it's the absolute value, because if you subtract, sometimes it may come out negative. So it's the absolute value. Okay.
Jacob, can I rephrase this in a different way?
Sure,
See
go
if
ahead.
you tell me if I'm doing it right.
Go ahead.
Okay, so this chart shows that there is a positive correlation between SR rating, satisfaction rating, and years of on-the-job sales experience.
Right.
And the moderator of training basically has no effect.
Right.
Whether or not they get training doesn't seem to make a whole lot of difference in the correlation between those two factors.
Correct. Right. So let's look here, because they're both okay. So now that we have that, right, because these were just the assumptions. So now that we've looked at the assumption and everything's okay, we can actually run the Ancova. All right. So let's go back here. And we go to Analyze, General Linear Model, Univariate. Now, we had already set up the Ancova, but now we have to go back to Model and put it back to full factorial. Okay? Click continue. And then we also have to remember is to turn off the split file, because this file we split up by training status, right? Because that's how we actually got the groups to compare, right? We compare the training to the non-training on the regression line, but we don't want to do that anymore. We want everything lumped back together. So we're actually telling SPSS, okay, we don't want the file split up like this anymore. We just want to look at everything together.
And where was that split command? I see it right there.
Yep,
Under data. Under data.
Split file, right? And you go back to analyze all cases, do not create groups. Okay, just click OK. And now we go to our normal options. Descriptive statistic, estimate of effect size, observed power, homogeneity of variance. Training, we only have 2 options, right? We only have 2 options, so we really don't care. But we can just do it for consistency. But if doing it is not going to mess it up, because there are only 2 groups, so it doesn't. Bonferroni is not going to kick in, but I just want to do this for consistency. Okay. And then now, if you have the e-means and you click on e-means, and then you would do this portion right here, right? This section right here is under e-means. E-M-M-E. There's an e-means button. Okay. So there's an e-means button. I think the save button is out, or maybe they dropped it or something. All right. So now what we're going to do is we're going to run this. Oh, I forgot to do one thing. The graph. We need the graph. Analyze, general linear model, univariate, and then the plot. So we're going to put the training on there so we can see the plot. It's always good to have a visual. And then we're going to highlight this. And we're going to run it. All right. So this is the mean rating for the training group. And this is the mean rating for the non-training group prior to controlling for years of experience. Okay. So this is prior to controlling for years of experience. Okay. All right. And we have Levine's equality of error variances. We're not worried about that because we have large sample sizes. They're above 30, so we're fine. So we actually have, we don't have to worry about this. And then we go on down to the actual test of between subjects effects. And what we're looking for here, so we go to years of experience. Okay, this is our covariate. Okay, and this is basically telling us that the relationship between the covariate and scores on the satisfaction are significant. There's a significant relationship, and the relationship is strong, right? Because 0.01, 0.06 is medium. For eta squared, this is small, and then 0.14 is large. This is 0.833. So years of experience has a strong impact on satisfaction scores, which we would expect, right? So adding that in is smart, right? Because I mean, the strength of the relationship is tremendously strong. So if you did not have that in your model, then what we're saying basically is that your satisfaction scores are probably more influenced by years of experience than they are the actual training, because the training only has a 0.37 size effect. So the effect of years of experience is almost double when you're just looking at the training. So removing that effect is very important, right? Does everyone see that? So the size of the effect for years of experience is 8.833, 0.833. Whereas the size of the effect for the training, whether or not you belong to the training group, is only 0.37. So it's this clobbers it. Years of experience is far more influential on satisfaction scores. So that's why you got to pull it out. You have to remove its effect. Is everybody following me with that? Does that make sense? Okay, great, great. Because basically what this is saying is that you don't almost even need the training. Just go by years of experience. But if you want to neutralize the effect, then we have to say, okay, now we're going to go down and we're going to say, hey, what happens when we neutralize the effect? Because we see that training is also significant. So there is a significant difference between the group that did not take the training and the group that did take the training. So what are the adjusted means when we remove the effect? So let me go back up here. So it was originally, it was 8.53. So this was 8.53. And then it was 7.80. 7.80. 7.80. Now, interestingly enough, for the training group, the mean actually lowered, right? So this was without controlling, without the control. We had a mean of 8.53. And then when we removed the effect, we saw that the mean actually dropped to 8.50 if you round to the second decimal place, okay? And then here we had without control, it was 7.80, and it just rose to some degree. It's a 7.84. So it rose 4/10. So basically what this is saying was that you probably had more people who had higher levels of experience in the training group than you did in the no training group, right? Because this score actually went down, right? This is the adjusted mean. So it's 8.50. So you probably had more people, we could probably actually run that too, who were in this group. So basically what it's saying is that, look, those who took the training had significantly higher satisfaction scores than those who did not take the training. Okay? When you remove the effect of experience. Okay? When you remove the effect of experience, that's what you get. And you can actually see that right here in the pairwise comparisons. All right? And you can see that right here as well. All right? Those who took the training got higher satisfaction scores than those who did not take the training. So whenever you're writing your results, you're always going to use the adjusted means, the estimated adjusted means, because these are the real means. You want to use the real means. Let me just highlight this. Okay. All right. So let's.
So Jacobs, where is the p-value here or the sig?
Okay. You got two sigs. The first sig is here in training,
Right.
right? And then you see the same sig down here when you go to the pairwise test.
Pairwise, okay.
Yeah, in the pairwise.
So this is adjusted for the experience when we do the
Yes.
pairwise comparison.
Yes. 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 This is adjusted for the.
Jacob?
Yes.
Sometimes I see that they'll add in, I guess, a covariate, and now something was significant that wasn't before, or vice versa. Does that have anything to do with what we're talking about?
That's probably regression,
Okay.
because what this does is it tells you up here. It tells you up here whether or not it's significant. This is like the last step, right? So with a regression, it's done stepwise. With Ancova, everything's done in one step,
Mm-hmm.
right? So if it wasn't significant once you controlled for this, then this would be 0.05 or greater. Like there are no steps here. Okay. So let me give you an example. So in a regression, the way you would run this, the same analysis is you'd run it in steps, right? Step one is you put in the covariate, right? Because you want to remove the effect of the covariate. So you put in the covariate. All right. And then step two, you put in the independent variable. Okay. Now the covariate may be significant, but then when you put in the IV, it might not be significant anymore, but the IV will remain significant.
Does that mean you drop the covariate out of the model?
No, it just means that the IV is probably sharing a lot of variability with the covariate,
Uh-huh.
right? So yeah, so generally you see things start to become significant and not significant when you're putting in multiple variables, when you have multiple IVs, right? So let's say you had IV1. So let's say we had training. I tell you what, if we did it like this, let me show you. If we did it backwards, so let's say our theory was, you know what? We're gonna put, we're not gonna have a theory. We're just gonna say the IV. We're just looking at the relationship between the independent variable, years of training, and satisfaction. Okay. We see that that has a strong relationship, right? Very strong relationship. And it's a high, but then we put in step two, we put in years of experience as another IV instead of a covariate. So that's IV2. The relationship between IV1 is going to weaken because the relationship between IV2 is stronger, right? Because we see that here. It's a stronger relationship. So the relationship between these two is probably going to go down. I could probably run that really quickly, but I don't want to. When we get to regression, I'll do this over again so you can see it. Okay, but I don't want to hold you on too nights because we still have to get to the. We still have to get to this. But generally speaking, when you run a stepwise regression, where you're putting in variables one at a time, that's when you start to see things change that are significant and not significant. Does that make sense?
Yeah.
Okay. But here, everything is going in simultaneously.
Okay.
Yeah. So you don't get that with that. All right. So the way we write this, again, we just follow the instruction. What test was performed? An analysis of covariance. Let me make it a little bigger. What test was performed? An analysis of covariance was conducted to determine if there were significant differences in Salesforce satisfaction scores between those who took the company training and those who did not, when controlling for years of experience. The independent variable was training status, where 1 was took the training and 2 was did not take the training. The covariate was years of experience. You're just answering the questions, okay? The dependent variable was Salesforce satisfaction ratings on a scale of 1 to 10, where higher scores reflected higher satisfaction scores. Preliminary analysis were conducted to test for linearity, homogeneity of variance, and homogeneity of regression slopes. The results indicated that there was no violation in linearity, but there was a violation in homogeneity of variance. However, the sample sizes were large, so according to the central limit theorem, the impact of this violation is limited. Wu's 1984 robust Ancova check revealed that the assumption of homogeneity of regression slopes was met. So because we did not have that difference of 0.4 when we looked at the betas, we can assume that it was met because Ancova is a robust test, meaning that when you have violations, it can withstand them, right? ANOVA is a robust, matter of fact, I'm going to send you an article tonight in the recap that talks about all the different simulations that were done, the computer simulations.
So,
all right.
Jacob, but you are saying practically we don't have to do it, right? Because it is a robust test.
Well, it's robust unless the differences are greater than 0.4.
Okay.
Right? So if they get 2, if they're going in the opposite direction, you know, there's going to be a limit. Right? So you always have to test to make sure the differences between the betas is within 0.4.
Okay.
Yeah. Because, you know, they can get too ridiculous. But this, I'm telling you, the article I'm going to send you tonight is like some of this stuff. I mean, the distributions they tested were just strange. I mean, the flat distributions, all kind of stuff. But anyway, the results of the Ancova indicated that there was a significant difference in Salesforce satisfaction scores between those who took the company sales training, mean 8.50, standard error 0.07, because we use the standard error, right? We use the marginal means right here, right? We don't use the original means, we use the marginal means because these have been adjusted, all right? And we use the standard error. And those who did not, mean 7.84, standard error 0.07 after controlling for years of experience. And then we have the actual F value here. So we have F 1/87. So this is the degrees of freedom for the training, and this is the error degrees of freedom. And then we've got 49.92, which is the F value. And we got P is less than 0.001. And then we've got the eta squared of 0.37. The effect size was large, based on Cohen standard of 0.01 for small, 0.06 for medium, and 0.14 for large. Specifically, those who took the company sales training had significantly higher satisfaction scores than those who did not. Based on the results of the null hypothesis, the null hypothesis was rejected. And then we just put in the table here. So when you're ready to run an Ancova, all you have to do is go to this sheet. You can use the same table and just just paste all this stuff inside here. All I did was just double click this, go over to the first variable, scroll down to, I think it was, let me see, corrected total. So I go down to corrected total, scroll all the way over to eta squared, copy, and then paste, and you're done. Everything's right there. All you have to do is just write this report and follow the same template. Okay? I try to make it as easy as possible. Does that make sense? Does anyone have any questions? All right. All right. Okay, so tomorrow, what are we covering tomorrow? Tomorrow we're covering multivariate analysis of variance. So someone had actually brought this up when you have multiple dependent variables. So this is what we're going to talk about tomorrow when we have multiple dependent variables. Okay. So are there any questions? I'm going to send out that article on the simulations that shows what a robust test and how it's measured and all this other kind of stuff. You can use that too. It's a killer. I mean, it's a stealth killer. All right. Any questions? If not, it's about 9:05. You guys can call it quits tonight, and we'll be ready to go again tomorrow.
Good night, everyone.
Okay.
Thank you.
Take care.
Thank you. Good night.
Good night.
Thank you.